Dear students, in the previous class, we have discussed instrumental variable method of estimation in the simple linear regression model. And we have specified the method of instrumental variables as a method of moments problem. We have also seen that for a simple linear regression model with the one endogenous variable, one instrument is suffice. And also we have discussed the need for strong instruments. Otherwise, the standard error of the instrumental variable will be much larger. Also, many recent studies show that if the instrumental variable is not strong, the estimators will be highly biased, and this bias will not disappear even in large samples. So we will discuss later how to check for whether an instrument is strong or weak. That is a point which we will see later. Before that, in the present session, we will discuss instrumental variable estimation of a multiple regression model. Instrumental variable estimation of a multiple regression model. Multiple regression model. And it is an extension of the simple linear regression model. We begin with a case in which there is only one explanatory variable which is correlated with the error type. That is, one explanatory variable is endogenous. The other one is exogenous in the sense that it is not correlated with the error type. Now, the model is y1 is equal to beta 0 plus beta 1 y2 plus beta 3 z beta 1 beta 2 z1 plus u1 plus u1. In the simple linear regression model, y1 is equal to beta 0 plus beta 1 y2 plus u1. And we have suggested z1 as an instrument for y2. y2 is correlated with the u1. Maybe because there are many omitted variables in the model correlated with the y2 but included in u1. Now we have a multiple regression model with the two explanatory variables y2 and z1. We call this model or this equation the structural equation. The structural equation. We call this equation the structural equation to emphasize the fact that we are interested in beta, estimating beta j, which means that the equation is supposed to measure a causal relationship. Now, when we go beyond the simple linear regression model, we introduce some additional terminology to distinguish between endogenous and exogenous variables. Now, y1 is endogenous. y1 is endogenous because y1 is correlated with the u1, the error time. And y2 and z2 are, z1 are explanatory variables. And we assume that expected u1 is equal to 0. y1 is endogenous, y2 and z1 are explanatory variables. We also assume that expected u1 is equal to 0. We use z1 to indicate that the variable is exogenous. The variable is exogenous means correlation between z1 and u1 is equal to 0. z1 is exogenous in the sense that correlation between z1 and u1 is equal to 0. Now, we use the notation y2 to indicate the fact that it is endogenous and it is suspected to be correlated with the u1. y2 is suspected to be correlated with the u1. We do not specify why y2 is correlated with the u1. It may be because there are very many variables correlated with y2 but included in u1. So whatever it is, we assume that y2 is endogenous, y2 is correlated with u1, z1 is exogenous, z1 is not correlated with the u1. Now, as an example to this, consider the model, the log wage equation. Log wage is equal to beta 0 plus beta 1 education plus beta 2 experience plus u1. In this equation, wage is endogenous. Education is also endogenous because education is assumed to be correlated with the u1. Experience is exogenous. Education is correlated with the u1 because wage depends on many other factors such as ability. Ability is in u1 and ability will be correlated with education, so that education and u1 will be correlated. So experience is exogenous, education is correlated with the u1. Now if this y2 is correlated with the u1 and if you apply OLS to estimate the parameters beta 0, beta 1 and beta 2, you will get biased and inconsistent estimates. So we seek an IV for y2. We try to find out an IV instrumental variable for y2. And a question here is, since z1 is not correlated with the u1, z1 is not correlated with the u1, can we use z1 as an instrument for y2? Since z1 is not correlated with the u1, the question is, can we use z1 as an IV for y2, assuming that z1 and y2 are correlated. Assuming that z1 and y2 are correlated. The answer is no. Since z1 appears as an explanatory variable in this equation, z1 appears as an explanatory variable in this equation, it cannot serve as its own instrument. It cannot serve as an instrument variable for y2. Since z1 appears as an explanatory variable in this equation, then z1 cannot serve as an IV for y2. IV for y2. So we need another variable We call this variable Z2. We need another variable. We call this variable Z2 that does not appear in 1. That does not appear in 1. We need another variable that does not appear in equation 1. We cannot use Z1 as an IV for Y2, even though Z1 is not correlated with U1, because Z1 appears as an explanatory variable in this equation. So, the key assumptions that we require another variable Z2, and the key assumptions are expected U1 is equal to 0, expected Z1 U1 is equal to 0, expected Z2 U1 is equal to 0. Expected Z1 U1 0, Z2 U1 0. These are the key assumptions. Now, given these other assumptions, the method of moments approach that we have discussed in the previous class suggests obtaining beta hat 0, beta hat 1, beta 2 hat by solving sigma y1 I minus beta hat 0 minus y2 I minus beta hat 3 z1 I equated to 0. I is equal to 1 to n. Then sigma z1 I yi minus beta hat 0 minus beta hat 2 y2 I minus beta hat 3 z1 I equal to 0. I is equal to 1 to n. Sigma z2 I yi minus beta hat 0 minus beta hat 2 y2 I minus beta hat 3 z1 I equal to 0. I is equal to 1 to n. So we have a set of 3 equations in 3 unknowns. And solving this we will obtain the estimators beta 0 hat, beta 1 hat, beta 2 hat. And we call these estimators the instrumental variable estimators. The instrumental variable estimators. And remember this, if Z2 is equal to Y2, Z2 is equal to Y2, then you will get the same estimators as OLS. If Z2 is equal to Y2, the 3 normal equation corresponds to the 3 normal equations of OLS in the multiple linear regression model, and IV estimators will be same as OLS estimators. So this is the method of moment conditions we have discussed in the last class. Expected UI0, expected Z1 UI0, expected Z2 U1 0. And remember this, these are the sample counterparts of population moment conditions. Also, to estimate this, we require an IV Z2 to be correlated with the Y2. Z2 is the IV for Y2, so Z2 should be correlated with the Y2. But the sense in which these two variables must be correlated is complicated by the presence of Z1. the sense in which these two variables should be correlated is complicated by the presence of Z1. And to explain how these should be correlated, when Z1 is present, for Z2 to be a valid IV for Y2, we use what is known as the concept of partial correlation. The concept of partial correlation. And the easiest way to state the condition is that you write the endogenous explanatory variable as a linear function of exogenous variables and error time. You write the endogenous explanatory variable y2 as a linear function of pi 0 plus pi 1 z1 plus pi 2 z2 plus v2 with the expected v2 0, covariance z1 v2 0, covariance Z2 V2 0, where these pi 0, pi 1, pi 2, etc. are unknown parameters. And the key identification condition is that pi 2 not equal to 0. We regress y2 on z1 and z2 and keeping constant z1 appears as an IV in the first equation. We want to see whether y2 and z2 are correlated. So the identification condition here means whether z2 can serve as an IV for y2 is that pi 2 is not equal to 0. That is, in other words, after partialing out z1, y2 and z2 are correlated. This correlation can be positive or negative, but cannot be 0. Now, it is easy to estimate this equation because we have data on y2, z1 and z2. We can test the hypothesis that pi 2 not equal to 0 by using the t-test. By using a t-test, we can test whether pi 2 is equal to 0 or not. And if a heteroscedasticity is suspected, we can use heteroscedasticity consistent standard errors to estimate it. And this equation is an example of a reduced form equation, which means that each endogenous variable is expressed in terms of predetermined or exogenous variables only. This is a terminology taken from simultaneous equation models where there is a distinction between endogenous, exogenous, or endogenous and predetermined. Anyway, this is what we do. So we regress pi 2 on z1 and z2, and if pi 2 is significant, we will say that Z2, the IV for y2 is correlated with the y2. So we can check the possibility that this instrument Z2 is a valid instrument for y2. Now we can extend this model by introducing more explanatory variables. Suppose that we expand this model as y1 is equal to beta 0 plus beta 1 y2 plus beta 2 z1 plus etc. beta k z k minus 1 plus u1 k minus 1 plus u1 and z1 z2 zk minus 1 etc. are exogenous. y2 is correlated with the u1. Now, so since z1 z2 etc. zk appear in the equation, their share was there on instruments. So we require what is known as an IV for y2. Let it be zk IV for y2. IV for y2 zk. Then the reduced form is y2 is equal to pi 0 plus pi 1 z1 plus etc. plus pi k zk plus v1. And the identification condition is that h0 pi k not equal to 0. Pi k not equal to 0. So, if this null hypothesis is rejected, then zk share was a valid instrument for y2. And we assume that there should be no perfect collinearity between z1, z2, etc. zk, and also that there will be homoscedasticity in u1. u1 is homoscedastic, and there will be no perfect linear relationship among explanatory variables. These are the two conditions required, and this is instrumental variable estimation of multiple regression model. And remember this, initially we considered a simple linear regression model with one explanatory variable. It is endogenous, so z1 is used as a IV. Now we have only one endogenous explanatory variable, but in addition there are so many exogenous variables. So one exogenous variables, k minus 1 exogenous variables, but there is only one endogenous variable. So one IV is enough for estimating the parameters beta 0, beta 1, beta 2, etc. beta k. To estimate it, we use what is known as the moment conditions that we have discussed earlier. The moment conditions that we have discussed in the context of simple linear regression model.